Okay, so let's start see what a PyTorch is. So far in your homework, you haven't used PyTorch, but from the homework 3, we will start to use PyTorch because this is kind of the major programming language for deep learning. Okay, so what is PyTorch? So PyTorch is software kind of provided by Facebook. So you might heard about PyTorch, TensorFlow, Caffe. So these are kind of similar software that provide you the API that you can implement a neural network, especially a deep neural network, in a very convenient way. Okay, the main purpose of these guys is to make the 3 steps that we mentioned, the forward, the loss, and the backward, to be implemented in one line of code of each step. Okay, so this is the purpose of this type of software. So before we have PyTorch or TensorFlow, we need to implement the backpropagation like what we implement in homework 2 or in the previous class for 10 layers, 16 layers, 20 layers neural network. So you can imagine how painful it is. And then later, since we have TensorFlow and PyTorch, so everything became much, much easier. Okay, so if we go to PyTorch official website, so they provide you a tutorial, say the deep learning 60 minutes. Okay, so well, so of course we can have a full class like when you learn Java, C++, we have a full class say how to use PyTorch, but that's probably too much. So we just want to spend this one class to do this kind of induction of PyTorch. Okay, so after today's class, if you want to know more about PyTorch, you can watch this video. So this is kind of official tutorial, so it should be pretty good. Okay, so PyTorch is a Python-based scientific computing package serving 2 broad purposes. Okay, so again, so people use PyTorch for deep learning, but actually it can be used for kind of most of the scientific computing situation if we want to use GPU. Okay, so if you do some kind of computer graphic, you want to rendering something, so you can also use PyTorch for the GPU computation. Okay, so the first purpose is to replace, let me see. Okay. Okay, the first purpose is to replace NumPy. Okay, so everyone has used the NumPy before. NumPy is the default scientific computing tool provided by Python, but it uses CPU. And now we have PyTorch to replace NumPy for those kind of computation. Okay, so that will provide you much faster computational speed. So this is the one purpose. Another purpose is to provide a library to implement neural network. Okay, so you can see they are optimized for neural network, which is the thing you have learned so far. Okay, so and they say the goal of their tutorial is to understand the PyTorch tensor library and the neural network at the high level, and train a small neural network to classify image. So if you play with their official tutorial, you will understand this. I think through homework 3, 4, 5, you will understand these 2 goals. Okay, and today we just want to have the initialization of the knowledge of the PyTorch. Okay. All right. Okay. So first, I put this link here. So if you have your laptop ready, you can copy paste this link. First, the presentation, the PowerPoint I upload to our course website. And then now you can copy paste this link. So I think this is, personally, I think this is the best PyTorch 101 type of stuff in my mind. Okay, so we can copy paste to the web browser, and hopefully you see the same page as I show here. Everybody gets to this link? Okay. Meanwhile, please open an empty Google Colab file. Okay, like this. So empty Google Colab file. Yeah, from previous homework, I think you guys are quite familiar with how to make a new Google Colab file. Okay, basically IP1MB file. Okay. Okay, so the tutorial is actually not that long, so it is quite condensed and it has the comments, instruction, etc., etc. And today, the major purpose is to go through these examples. Okay, first, so in homework 2, you guys have implemented a 2-layer neural network from scratch using Python. And here they provide a version of implement a 2-layer neural network using Python. Okay, so you can do things like me. You copy the warm-up NumPy example. You can paste it to the Google Colab. Okay, and just click run, and you will see, yeah, the updates. So they're updating the weights and finish the computation. Okay, so this is pretty much similar to the homework 2 you have done. Okay, it's a 2-layer neural network. So now I give you probably 3 minutes to play with this example and to also play with the parameters, variables since you have already done the homework 2, right? So you have a better idea of how to implement a neural network, and now you can see what's going on here, and probably you have some questions. Okay, so 3 minutes. Please copy paste it to Colab and run this example. Okay, has everybody a problem of running it? Okay, this is pretty sweet, right? So pretty concise and well organized. So this is a kind of a beautiful written of a code. Okay, so for any parameters, you can print it or whatever to see what's going on. So this is basically how we implement things in Python. Okay, and let's go back to this. Share my screen. Okay. Okay, so now I copy paste the source code from the website to here. Okay, so first we use NumPy, of course. Okay, import NumPy, and we define the shape of all the variables and initialize x, y, and w. Okay, so these steps are initialization, and now we will have this line of code define the learning rate. Okay, remember the weights is the weight minus learning rate, loss to the W. Okay, so we define the learning rate. You can see we choose the learning rate empirically. You can put one e to the -5 here to -6. So this is a kind of empirical value. And then we will have a for loop since we are doing the gradient descent. So we will do 5 iterations here. And now we can see, okay, so they do the first forward layer. They define the ReLU layer, and they will get the prediction of Y. Okay, 2 layers. And here you can see they compute the loss. So this is number 1 step, number 2 step. And then they do the backward computation to compute the gradient of the neural network. Okay, so they compute the gradient of each variable, and then the scene we want to update are W1 and W2. So you have the learning rate, this guy, okay, multiplied by the gradient of the L. And look at this. This is minus, and then minus itself is update. Okay, beautifully, the 3 steps we introduce, 1, 2, 3. Okay, forward, loss, and backward. Any question about this? Perfect. Okay, now let's see. Remember, the first purpose is that we can basically replace almost all these computation using PyTorch. Okay, so now instead of loading NumPy, we load PyTorch. Okay, so we import PyTorch. Then we put these command. Okay, this is really important. So we can say, okay, in this time, if we want to use CPU and the GPU. So if you say CPU, it will be pretty much similar to NumPy. But if you say CUDA, which is GPU, it will run much faster. But you need to have a GPU in your computer. Okay, so you need to specify your device this time using PyTorch. And then same, these 2 lines are the same. Okay, so define the shape and look at this. So previously we use NP random, and here we use torch.random. So it's kind of a random number. All right, and the other things are the same. Okay, shape is the same, but now you need to specify the device. Okay, so this is the difference. Now you are using a different command or function. Okay, because now we are using torch rather than NumPy, but the remaining things are pretty similar. Okay, and you need to specify the device. And for the W, same thing. Okay, you specify the shape, you use torch random initialization and specify the device. Next, learning rate, exactly the same thing. There's nothing related to NumPy, so we use the same learning rate. Okay, so now we have finished the initialize step. So if we call it initialize, so now we finish the initialize step using PyTorch. Okay, so this is in format is pretty similar. Now we just use torch dot something rather than np dot something. Okay, again, we want to have 500 loops for the optimization. And now you can see in the NumPy, we use, since X is a NumPy array, we use NumPy X dot, here use XMM. Okay, so basically same thing, dot product. Okay, so we use, they define ReLU and they use NP maxim. NP maxim is similar to the clam function in the PyTorch. And again, dot product, we use MM. Okay, so for this kind of stuff, there is no way to learn it. So they're just the most efficient way just to Google. Okay, Google what is dot product in PyTorch, what is the maximum function in PyTorch, and you will find that page. So they make the API really easy to Google. Okay, it's just some kind of definition, nothing fancy here. And by doing this, we basically migrate our forward loop to PyTorch. Okay, so number 1, forward. Okay, any questions? Okay, then number 2, loss computation. All right, so basically still nothing fancy. In the Python, we use NP square to compute the square. In PyTorch, we use power to compute the square. It's just a different format, okay? And the sum is the same. And you can print your loss. Print your loss is the thing you play with. For example, you see the number go one by one. It's just you print the loss. Okay, so now we finish the step number 2. The number 3, we can see what's going on here. Number 3. Okay, so this is basically the same, right? So this is just the product, and the transpose in NumPy we use dot capital T. In PyTorch we use dot T parentheses. Then dot product, if you remember, dot product is here. Then dot product and here they copy the gradient. And in NumPy it's called copy, the function. In PyTorch is clone. So basically the same thing. And then they apply a threshold for ReLU. Eventually they have the dot product, okay? And these 2 parts are equivalent, nothing changed. Okay, this example just give you a feeling, say, the first purpose of Torch is just to replace the functions in NumPy. Okay, and if you set the device to be GPU, now you can use GPU to compute the exactly same thing with much faster speed. So in the toy example, you can copy the right side of the code from the website to your Google Colab and try if you see different speed when you type in CPU or GPU, okay? But we will not do that in class. You can try it later. Okay, so this is how we migrate a NumPy to PyTorch. This shows PyTorch, the first aim is to replace the NumPy for GPU. Okay, any questions about this example? Okay, great, pretty straightforward, right? So now we know the first goal, and then we see the second goal, okay? Second goal is to provide a convenient way of implement a neural network. And eventually you will see this guy will become one line of code. Sorry, and this guy one line of code and this guy one line of code. But in the middle, we will introduce several versions to go to the final version gradually, okay? All right, first let's put the Scratch version, NumPy, Scratch version, PyTorch here, and then we will see how can we use PyTorch to make the neural network implementation easier. Okay. All right, so first, we can keep all these guys the same and implement the W1, W2, okay? So in this time, look at the difference. What is the difference? Yeah. Sorry. Yeah, so I think you can look at your PowerPoint rather than, because you can see the quality of the projector is not good for the code, right? So that's why I say you should see the course slide. There is no way, even for me at that distance, it's difficult to see the text. Hopefully this is a LED screen, right? So rather than a projector. So, but this is what it is. Okay, so W1 and W2, do you guys see any difference? Yes, so now we have this, right? Okay, so interesting, right? So why don't we have this for X and Y? Why we only have this required gradient for W1 and W2? Why we keep the same for X and Y? Any answer? Sorry, can you speak a little bit louder? Yes, so if you remember in the neural network, what we try to optimize is the weight. right? So we want to optimize theta or W, whatever the name is. We don't actually optimize X and Y, right? X and Y are the things we know. We provided the neural network X and Y and let it fit W. So that's why we don't need the gradient for X and Y, right? We never compute the gradient of X and Y. All right, so we never see like X equals to X minus something to X, right? So because X is just the constant, what we want is W. So that's why we need to have the gradient of W. So it's called required gradient. So this is the beautiful thing. So later, probably you can realize how beautiful it is. Okay, then, okay, there's nothing fancy. They just concatenate these three line of the code to one line of code. Okay, one following another. There is nothing different here. It just show a better, more concise implementation. Same thing here. Okay. Then let's see the backward. Okay, in this time, backward has huge difference. Okay, so in this time, look at the weights update. Okay, look at this. All right, so W1 and W2 can be updated by this guy. And using PyTorch, we get the gradient automatically. So we no longer need these guys. Okay, so remember, so the backward part is the most painful, right? The forward part is that you just do the dot product and use ReLU. But the backward is really, really painful. If you have many, many layers, so you can imagine this piece of code will be extremely long. But with PyTorch, this is gone. Okay, you just need to use W1 gradient, W2 gradient, which means after you do the step 1, you do the step 2, and they will compute the gradient for you automatically. Okay, this is a big breakthrough, and this came from numerous smart and expensive engineers. Okay, so we should appreciate this kind of convenience. Okay, so this is this is kind of the second goal of PyTorch. If we go back to the previous slides, is that now we have a much simpler way of implement neural network. And this is impossible in NumPy. Okay, so if we want to get rid of this, this is impossible for NumPy. But if we use PyTorch, okay, if we use neural network, again, this is for neural network. If we use SVM or whatever, you cannot use this. But if you use neural network, they can compute the weights for you automatically. Beautiful, right? So that is the reason I say, well, the math we did in the previous class, this basically the once per life experience, because when people get this, no one wants to do the math again. Okay, and we don't actually need to do the math again. And from today's class, you barely see the math. Okay, any questions? Okay, beautiful. So this is the beautiful thing of PyTorch. Okay, so I put the full version of a 2-layer, you can see 2-layer neural network using PyTorch like this. Okay, this is kind of almost great. So if you write your code like this, send it to a manager, I think it's okay. So no one would criticize your code. But remember, we can use one line of command for each step, right? But here, people would say, okay, you basically cheating. You basically merge 3 lines of code into 1 line, right? It's not actually 1 line of the code. Think about it, if you have 100 layers, this line of code will be extremely long, right? You will have dot product claim, so you will do like 100, 200 times, okay? To do this, PyTorch provides a beautiful mechanism is that you can define your model in a separate function. Is called NN sequential. Okay, so the NN sequential, look at this is called NN sequential. Probably it's too small on the screen, but if you look at the slides, you will see NN sequential. NN sequential is tell PyTorch, okay, I want to build a neural network with the following layers. The first layer and the order matters. Okay, remember, please notice that the order you put here matters. The first line within the NN sequential is the first layer. The second line in the N sequential is the second layer. Okay, so now I tell the network, the AI, say, okay, I want to build a linear layer. I want to build a ReLU layer. I want to build a linear layer as my neural network. Okay, so think about if you have more ReLU layer, linear layer, etc., you just add these lines of code here. Okay, so this is much, much more beautiful and more readable than this. Okay, so this is also important for industry, okay, for commercial software. The companies pursue a way that your code can be easily digested by another engineer's code can be easily digested by you. So if everyone writes their code in this way, well, probably it's good for you, but it's definitely a nightmare for another engineer who kind of follow your work for another function. But if we give a specific definition here and write the layer by layer, I think, and if you have played with PyTorch and you see another people's code, you can basically even draw the neural network layer by layer by seeing their code. Okay, so compare with this guy, compare with this guy, okay, compare with the single line version. This is much more beautiful and well organized, right? So for this guy, well, if you know the math in our class, you know, okay, this is a linear layer. But for the people who haven't learned deep learning or neural machine learning, they have no idea why we have a dot product here, right? But if you implement explicitly, say, this is a linear layer, this is a ReLU layer, that's it. And these are defined by PyTorch. Okay, you cannot change the name, say, ReLU, whatever, small letter. So these are defined by PyTorch. Okay, so this is very important. So if the software gives you some standard way of defining something, it's very easy for another engineer or another data scientist to understand your code. Okay, any question about this part? Yeah. Sorry? Yes, yeah, you can see the comments, okay? So I think they explained in the comments. Okay, so the no-grad means the context manager to prevent the PyTorch from building a computational graph for the update. So in the real version, you in the 2 slides later, you will see what's going on. Okay, that's a great question. All right, so now we finish basically the forward loop, and then if you see any major PyTorch code online, you will see this. Okay, so this is what I said, one line of code for step 1 forward. So people will call your network model. If you look at online code, most of the case they will call it the model. And the model X your input, Y predict your output is basically a neural network. Whatever it is, you give X, you give a Y predict. Okay, so just one line of code, and you define your network beforehand. Or a more common practice is that people define the model as a separate Python file. Okay, and in that case, you can build your model zoo if you define your model as a separate Python file. For example, you can build a 2-layer network called network 1, and in the main function, you just load model 1, and again, use the same code for the remaining thing. You can build a 3-layer, you can build a 2-layer with the wider nodes of each layer, whatever. So that will make the code reusable. Okay, in the main function, typically what we see is just these guys. Okay, then the second step, number 2, one line of code. Typically, people will define a loss function beforehand. Here, you can see we use MSE loss, and here is the mathematical expression of MSE loss. Now we don't need to explicitly define the difference, power of 2, sum, those kind of stuff. And the PyTorch provide maybe now 50 or 60 different standard loss function you can use. Okay, again, the yellow color, the MSE loss is provided by PyTorch, not provided by me. And we cannot change the words here. That give us a very good standardization. Okay, now you don't need to implement this. I say, oh, I want to use MSE loss. So now you can imagine if we want to use cross entropy loss, right? So we can just say torch.nn, then cross entropy loss. That's it. You don't actually even need to understand what is log, what is P. Okay. Then this is zero grade. Okay, so zero grade means at each iteration, we clean up our memory of remember the grade. This is some hardware issue, right? So this is not quite important. You just make sure you have this in your code, that's it. So they just want to clean the memory, do the iteration, clean memory, do the iteration. Otherwise, the gradient will accumulate with each other. In some cases, we actually don't want this, but this is typically in research field. In the engineering field, we typically need this, that's it, okay? So this is default. Here, look at this. So this is number 3, the backward. Okay, now, so basically everything become to these two guys, okay? So these two lines of code become the loss backward. And the beautiful thing is that this is the same for any neural network. So no matter you use 2 layers, 3 layers, you don't actually need to define this. You just do the loss backward. This is same for any neural network. For the modern neural network, for whatever neural network, it's the same thing. The number, so the PyTorch make the previously most complicated step, step 3, to be the simplest step. Okay, just the dot backward. Then this is how you update your parameters. Okay, so now if you look at any Python code for, sorry, PyTorch code, you will probably have a better understanding what's going on. And if you see the major PyTorch networks online from GitHub, you will see basically almost every people follow this workflow. Model, loss function, zero grade, backward. Super, super easy and convenient, okay? All right, any question about this? So now, this is the OK version, and we commit to a grade and the standard version of PyTorch. Great. Okay, so left side was the beautiful version that we saw, and now the right version can make it even more concise, okay? So first, same thing, okay? So the model, same thing, okay? Loss, same thing. Learning rate, same thing. Now we define an optimizer, okay? So the optimizer is to replace this, okay? In this version, there is still some like a multi-line code here, and the PyTorch make it even simpler. Say, you just tell me what do you want. So this is use Adam. Adam is a better optimizer than SGD, and we will cover it later. But if you want to use the exactly SGD in your code, you just do torch optim. This is kind of implemented by PyTorch, SGD, then let's replace this. So now you can easily change your MSE loss to cross entropy or another loss. You can easily change your optimizer function to another function. You can easily change your network to another network. Now, the deep learning algorithm is kind of the Lego building, okay? So you just play with different components. You don't actually need to implement the detail, even for this step. Now it's become one line of code. Optimizer step. Just tell the network now I want to update my weights for this step. Okay, so if you get rid of the gray text, gray comments here, you can see now your code is basically 4 or 5 lines of the core piece of the, yeah.
There's no device, I
Yes, I think if you go to see the example, probably they initialize the device at the beginning. So they say this is GPU computation. So I think I just screenshot some portion. You can go back check. I think this code can be run in GPU. Yeah, that's a great question. Yeah, so they just make the code further concise and simple. Okay, so their goal is to make it as simple as possible, but also as standardized as possible. Okay. Okay, any question about this? So now we basically change all the complicated stuff into 3 or 4 lines of the code. All right, is that beautiful? All right, so this software spent, I don't know, billions of dollars. I don't know how expensive it is, but it's actually the great effort from hundreds of awesome engineers and scientists. Okay, so I personally really appreciate it because when I start deep learning research study, I need to implement all the stuff, even using C++. So now it's very, very convenient. Okay. All right. So here is the version, the concise version that we have. Okay. And here is that, so this is even the more standard thing that I say. You can define your network as a class. So this is, you can copy paste this part into another .py file called 2-layer net.py, whatever. Okay, you can further standardize. If you put your model together with your remaining code, it looks like this. If you put your file into a separate class or separate Python file, you need to follow this format. So this is still nothing fancy. For each network, we have initialize and forward 2 pieces. So you can see the initialization, basically same thing here. And for the forward net, so basically the same thing here. Okay, so which means if you want to define your code in another separate class or separate Python file, typically we will follow this format. And again, this is required by PyTorch, so we don't change the design. You cannot say forward 1 or forward 2. This is just called forward. Okay, if you change the name, they will not recognize your code, and you cannot get the gradient automatically. Okay, so then the remaining thing will be the same. Model, loss, 0 gradient, backward, step. Okay, 5 lines of code. Okay, and then now you can see if you define your model in another separate file, you can easily switch your network, right? So here we define the model explicitly, and then now we define our model in this orange color. Now you can switch your model as you switch the loss and the optimizer. So now you can download a network from PyTorch, download a network from whatever lab, download a network from whatever company, and just copy paste the py file to your folder and change this 2-layer net to their whatever net, maybe ABC net or ABCD net, whatever net. So now it's very convenient. Okay, so this is the final piece of how to use PyTorch to implement a neural network. Okay, so in that way, you can imagine, okay, now we don't afraid of a network with 100 layers, right? We just say, okay, now we will have 100 layers here. Okay, so you just write linear, 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 that's it, okay? And you define your layer and put that into the forward loop. So everything will become easy to read, easy to understand, and scalable. Okay, so any question about this part? So we see the history of how we optimize a NumPy code of two-layer neural network, which we used before 2015. So that is how we do research and do the R&D. Now, this is the latest and the current practice of how to use PyTorch to develop a deep neural network. Yeah. TensorFlow. Sorry, I cannot hear very clear. So I understand you're asking why there is some definition for torch, right? So is that this part? Yeah, so the reason is that if you copy paste this, the left side to a separate Python file, you have no way to load it to you put that as a Lego to your main function here. So you can, if you define with your main for loop, you can define your model like this. But now the idea is that we want to make the main function as simple as possible and put every component as a piece that we can plug in and play. So. Yeah. Yes, yes. So here, this is sequential. So in the forward pass, the order matters. The order should be exactly as the n sequential if we want to define using n sequential. Yes, so they kind of changed the n sequential to a function called forward. They're basically same meaning, right? Sequential is forward, forward is sequential, same thing. Okay, forward means forward pass. Backward means backward pass. Loss means loss function. So it makes everything consistent with the concepts, even for the name. Okay, great question. All right, so any more questions? Yeah, if you have any questions, please feel free to say that, right? So your question probably might not be everybody's problem, but at least 30 or 40% of people will have the same question as you, right? So that is a good practice to solve the problem in the class. All right, great. So now we see what's going on. And actually, you guys have already implemented this, okay? So if you go back to homework 0, okay, so we don't need this. So if we go back to homework 0, have you guys actually see what's inside the homework 0? What is the network? So if you see that, you will realize you actually have already implemented that, okay? All right, so let's see Google Colab. Okay, so we have this example. Okay, so I think you guys have played with this example, and you can see, okay, import torch. Okay, what is the main function here? Okay, run man.py. Okay, let's see what is man.py. Oh, man.py probably has defined in this function. Oh, I didn't put the man.py in this folder, but I think in the homework, I have the link to the man.py. Okay. All right. Yes, let's go to this example. Actually, this is official PyTorch example to do the image classification for MNIST. Okay, so let's see man.py. Okay. All right, now you kind of understand what's going on here, right? So they define a class called the network, define each net layer. So we will cover later in the semester what is convolution layer, dropout layer, linear layer, but at least you understand the linear layer here, okay? Then they use a forward function to assemble different layers, like the sequential, now they use forward. Then we go to the trend part. Trend part, you can see device, right? You put the thing to device. You do the optimizer zero gradient. You do, this is your forward. This is your loss. Okay, so then you see they use NLL loss, softmax. So softmax is the softmax you learn. The NLL loss is the cross entropy loss you learn. Then they compute the loss, do the backward. That's it. And then you print the loss at each iteration. Okay, so this is the main part of homework 0. So basically, actually, you have already practiced the PyTorch version of how to implement a neural network. Okay, so if you're interested, you can go back to play with your homework 0 again to see what's going on here. Okay, any questions? All right. Okay, so here is another additional tutorial that you can see what's going on in the gradient. That's the core piece of the backward. Okay, so I think by this slide, we have covered the best practice PyTorch 101 that I think step by step. Okay, next, we go back to my favorite example here. Okay, we implemented at least the 3 versions of this guy. Okay, so we do the naive math. Okay, we do the more concise backpropagation, and we do the third way that we build the forward graph, backward graph, and compute this. And now we will see how we compute this using PyTorch. Okay, so after you see this, you will never want to do the previous 3 ways again. Okay, so let's go to this way. Okay, so first, this is our initialization. We have seen this many times. Probably you guys have already remember the prediction is 0.191. Okay, so you probably have already remembered that. Let me probably make this larger to see the numbers. All right, so now I will show my example. So we play with the example from online resource, and now I will show my example of this guy. Okay, so now please follow the code step by step with me. Okay. First, we don't need this anymore. Looking at the code here. Okay. So ready? Have your collab ready? Good. Okay. All right. First, let's import torch. Okay. This is a very beautiful step. Import torch. Okay. Yeah, hopefully we can import torch. No problem. Okay, then let's define, we add the code. Let's define the inputs. Okay, I1 equals to 2 dot. Oops, we don't want to have this guy. I2 equals to 3. Okay, with this dot, we tell the computer we are using the float rather than the integer. Well, you can explicitly say MP float or torch float, whatever. But now we use this simplified version. Then the first step, we need to convert a NumPy number into a PyTorch number. In PyTorch, it's called tensor. There's nothing fancy about tensor. Tensor is just the variable matrices. Okay, you can regard another software equivalent to PyTorch is called the TensorFlow. Okay, so they basically just convert the NumPy into a tensor. Okay, I2 equals to torch tensor I2. I can make it larger actually. So let me make it larger. All right. All right. Okay. Hopefully this is better. Okay. So torch I1, torch I2. Okay. Then we write, and of course we can see what's going on. Okay. We can we can print whatever I1 equals to float I1 and print I2 F I2. Okay, so it's very important to see what's going on. Okay, it will tell you the tensor is 2, the I2 tensor is 3. Okay, so this is kind of the thing we have. Probably we need to use this guy. Let's see. Yeah, so this is what is the correct way. Okay, percentage. So now you see I1 equals to 2.000, I2 equals to 300. So this is exactly same as this guy. So we initialize network with 2 and 3. Okay, so then we add a line of code. Yeah, actually we can add many lines of code. Okay. Then let's see what's going on for H. Okay. So now let's do the forward pass. Okay, forward pass. To do the forward pass, we need to initialize the 4 weights. Okay, W1 to W4. So we initialize W1 equals to torch. So now we do a more concise way. Okay, we no longer need to define it in 2 lines of code. We can directly define things here. And remember, since we want to get the auto gradients, we need to do this. Okay, we need to do the requires gradient 2. Okay, then we can do W2, W3, W4. Okay, so again, the copy paste is very important for programming. So you don't want to retype everything again and again. Just copy paste, change the thing you want to change. 12008. Okay, so this is whatever these 4 numbers are. Okay, 11, 11, sorry, 11, 21, 12, 8. Okay, 11, 12, 8. Okay, then we can write. So now we have the weights. Then we can compute H1 and H2. Okay, now we have the number, but actually it's computed from the input and the weights. Okay, H1 is W1 multiplied by I1 plus W2 multiplied by I2. Okay. Again, reuse the code, then we can see H2 equals to W3, oops, W3 multiplied by I1, W4 multiplied by I2. And then if you are very lazy to write code, you can copy paste and print print H1 and H2, see what's going on. Okay. All right, but yeah, magic thing happened, right? So we get 0.85, we get 0.48 here. Okay, everyone finish this step? Okay, hopefully everyone are good until here. Okay, so now next thing, so we compute this guy. The ultimate goal is to compute a prediction, but we still need to define W5 and W6. So let's copy 2 lines of code here and define our W5, W6 as the number we plot in the figure, say 1, 4, and 1, 5. Okay. 1, 4, and 1, 5. Again, the weights are initialized randomly. Okay. Then we can click run. Now we have the W5 and the W2. Eventually we can compute the prediction. Prediction is a combination between H1 and H2 with W5 and W6. So we have prediction equals to W5 multiply H1, sorry, multiply H1 plus W6 multiply H2. Okay, then we can see what's going on. Again, copy a line of code here. Instead of showing age, now we want to show prediction. Hopefully it's magic 0.919, okay? See? Oh, beautiful, okay? 0.9191, okay? Great, any questions so far? Yeah. Okay, perfect. So this is like kind of at the beginning of why you initialize I1, I2. You mean why is dot is to tell this is a float? If you don't have this, probably they will regard as integer. So every time you only get the integer, you will never get 2.1, 2.2, something like that. Okay, great question. Okay, any other question? So now we basically compute all the numbers in this graph. Okay. Then this is the step one. Okay, we do the forward. This is exactly how computer do whatever 100-layer complicated network. It will just do this kind of things one by one. Okay, use your current weight to compute the prediction. Now we go to number 2, loss. Okay, remember we use MSE loss, so we need to have a half here. Then you use the chew. The chew is 1. Okay, remember the chew is 1 here. So we input 2, 3, the chew is 1. Minus prediction, minus your prediction, and do the power of 2. Okay. Then we can compute loss. Loss to F the loss. All right. So now the loss is 0.327241. Okay, so if you go back to see the slide in the classroom, so it's exactly the same value. So I don't put it here, but if you go back to see the slide in the previous class, this is literally the loss. Okay, let me go back to add a few more lines of code. Okay, let me make it smaller. The code. Okay, so now we finish the step 2. Then we need to do the third step. And then now we don't need any mass, gradient, those kind of weird stuff. Now we just do the backward, okay? Okay, finish, okay? We basically finished the forward, loss, and the backward. Then we can see how can we update the weights, okay? And now let's try this, okay? So now you can type any weight. Let's see, W4. So first, let me go back to here, okay? So from the computation, we manually compute the weights from our previous example in the class. So we see these are the values after we put H, delta, alpha into this function. And here is basically the weights inside the parentheses, okay? The number inside the parentheses. We haven't touched learning rate yet. We now need to compute the things inside the parentheses. And the 6 numbers we did in the classroom are this. So if you go back to see the slides, and now we don't need to do any computation. We just do W4. For example, let's see what's going on for W4. W4 gradient. Okay, this guy. Okay, negative 0.3641, negative 0.3641. Okay, even W4 is here. Okay, remember in the previous example, we need to compute these 2 guys, then compute these 2 guys. And after the backward, they have already computed all the gradient for you. Since if you have 100 layers, millions of gradient, you can show gradient of any weight. Okay, then the remaining thing will be the old weight minus a learning rate multiplied by the W4 gradient. Okay. So if you do the math here, so I2 is 3, delta is negative 0.809. The W6, we already got W6 is 0.15. So you can basically manually compute the things here. It will be the same. Okay, 3 is the I. Okay, the next thing is negative 0.809. This is difference between your prediction and the truth, and multiply by your current weight 4. You can basically get the same thing. But here, if you use PyTorch, you don't need to worry about those mathematical expression again. Okay, so think about this is a very simple example, but if you have ReLU, if you have multiple layers, you have hundreds of nodes, this way will become very painful, and we definitely prefer the auto-grade. Okay, so far, any questions? Yes, 3 is the I2. Okay, this is delta is 0.191 minus 1. So this is delta. This is W2. W2 is whatever you initialize here, 0.15. This is the mathematical way to compute the gradient in the parentheses. I2 multiplied by W multiplied by W6. This is actually a very good question because this will be very likely in the midterm. Okay. Yes, delta times W. Not a delta W. Yeah, it's delta times W. That's a great question. Okay. They should have a dot here, but this is basically multiplication of 3 guys. Yeah, so this is a very good question, right? So because this can be confusing, right? So why do I have that delta? Delta is actually 0.191 minus your 2 is 1, okay? All right, we forgot about this. We don't need this, okay? So in this example, we just need the gradient, okay? Then again, like we said, we need to define a learning rate. So now we can give it a very random number, 0.05. We define a learning rate. Then we can update our weights. Say W1 equals to W1 minus learning rate multiply W1 grad detach. Okay. So this is the same thing as the zero gradient in the function. So we want to, let me make it smaller. Yeah. So once we get a W1, we want to do the detach. Otherwise, it will change for other W. So this is kind of the standard operation. But the basic idea is that now you update your weight using the learning rate you define and the auto grade that PyTorch provide you for free. Okay, so that's a big breakthrough for computation. Okay, and now we can print what's going on for the weights. Okay, so we can print the new weights here. W1, W1. Okay. All right, so now we have the updated weight. Okay, so after one iteration, your weights become this. This is different from the previous iteration that we see here. It's no longer 0.1121. Now it's changed to 1222, change a little bit, but hopefully these new weights will give you a better prediction, which is more close to 1. Okay, so with this new one, then we can do the forward loop again for the next iteration. So typically we write a for loop, but here we just see what's going on in after one loop. Okay, Oops, so let's copy paste these two lines of code. So now we have the new W and the W2. If we suppose we still use 2 and 3 as input, hopefully we can get a better prediction. So let's copy the prediction. Okay, so now you can see in the iteration number 2. So typically we implement this as a loop, but now iteration number 2. So we just show what's going on for one iteration. Okay, so now you can see to compute the new prediction, we need a new I1 and I2. So basically, if we keep it as 2 and 3, that's fine. And we need to have the updated weights from this guy. And then we can print what's going on for prediction. Print prediction. Prediction. So if you remember in the classroom, it would be 0.25-ish, which is more close to 1. Okay, now we have 0.25-ish. And if we implement as a for loop, implement the entire thing we type in as a for loop, you will see eventually you will have a prediction that is close to 1. Beautiful, right? So if we don't have PyTorch, right, the most painful backward part, we need to write many lines of the code and very error prone. But here, we don't need to do anything. We just define the forward path. We define the loss, then we directly use the dot backward function provided by PyTorch, and it will do the ugly math for us and compute all the gradient for all the weights, no matter it's in the middle layer, last layer, first layer, whatever. It will compute the weights, compute the gradient. And once you have the gradient, you just do these things to update the weights. Okay, so now zero math. Okay, zero math. If you understand the multiplication, if you understand the dot product, that's all the math we need for deep learning. But still, I think the previous class are valuable. If we directly show this in the first class, you will never have idea what's going on. So why these are beautiful, why we need this, you will think this is just like this when the program was invented. But actually, it has been a 10 years progress that now we finally can do things like this. Okay, beautiful. 2 more minutes for this class. If you guys have any other questions. So that's the end of the example. This is my personal example. Okay, so I think this is a good example to show the auto gradient, which is the most important part. You want to see the final prediction? So if you get this number at the end, that means you have done all the previous steps correctly. Okay, that's pretty much the case.